WWT presents Briefings.
Hello and welcome. My name is Mike DiVincenzo, and I'm here to talk to you about SR-MPLS in the enterprise. I'm a technical solutions architect with Worldwide Technologies. I've been here 6 years. Prior to that, I spent 14 years in advanced services at Cisco Systems, and I've been at CCIE for over 20 years now. So let's talk about SR-MPLS in the enterprise. But before we do that, we need to talk about SR-MPLS in general. So let's go through an overview of SR-MPLS. So what is segment routing? First of all, segment routing was invented by Clarence Fisfus from Cisco Systems in 2013. It was a follow-on to MPLS. It's a simple stateless mechanism to program the path the packet takes through the network. It is often referred to as the evolution of MPLS in the programmable network. One of the huge advantages is we can use the MPLS data plane without any modification. And segment routing is less complex, uses fewer protocols, and it's easier to monitor and manage than MPLS. And in addition, we get native IP fast reroute. So why segment routing? Simple, automated, and scalable. No additional protocols. It uses straightforward extensions to ISIS and OSPF. It leverages existing MPLS services and hardware. It offers topology-independent fast reroute, which means we can converge in less than 50 milliseconds. We get unequal cost load sharing, both centralized and distributed traffic engineering. We also get delay and constraint-based routing, along with service disjointness from the same or different head end. And this is all accomplished very simply with what we call on-demand next hop, or ODN, with automated steering. So some of the advantages and business drivers of segment routing. We get increased resiliency and uptime because fast reroute ensures minimal downtime. We get efficient use of the network through traffic engineering by utilizing all links. We get a more agile and flexible traffic engineering with diversified and stringent SLA support for mission critical traffic. Very much different than our traditional and classic RSVP TE. We also get a simplified operational model, which reduces OpEx and provides a seamless transition from legacy MPLS. So any box that supports MPLS can do segment routing. By using a centralized controller, we can adapt to the multitude of business requirements, and we provide versatility, scalability, and virtualization through doing that. And we also get an improved user experience because in addition to QoS, we get centralized bandwidth optimization, and we'll talk a little bit about that later. So looking at the architecture of segment routing forwarding state is established by ISIS and OSPF. So what we have is perfect integration with the routing protocol, not a separate protocol like LDP or RSVP like in the past. So there's no synchronization between protocols that's necessary. It's also agnostic to the forwarding plane. It doesn't care if it's MPLS or IPv6. Now this presentation is strictly on SR-MPLS, but there is a version of segment routing that runs over the native IPv6 data plane, which has some huge advantages. Again, when we're doing SR-MPLS, we're doing MPLS without any modification to the data plane. We do all the same operations we did, and we often refer to as a segment as a label, but it's basically the same thing. So segment routing is often referred to as source routing. Actually, the original RFC is labeled source routing, and it's done so because the path of the packet is encoded by the head-end router as an ordered list of segments. So then the rest of the routers or devices along the path are just executing the instruction encoded by the head-end router, which makes for ultimate scalability. And again, a segment, and in this case, a label, is an identifier of any type of instruction. And that instruction could be a forwarding instruction, which is how to forward the packet across the network from point A to point B. Or it could be a service, a layer 2 VPN, a layer 3 VPN, or it could be something even more in depth than that, especially when we get into SRv6. Again, in the segment routing architecture, MPLS is an ordered list of segments represented as a stack of labels. There's no difference. Segment routing uses the MPLS data plane. So that means we have very seamless migration from an existing MPLS network to a segment routing network. And this is applicable to IPv4 and IPv6 address families. So we can transport IPv6 and IPv4 over an SR-MPLS network. And again, we know this as SR-MPLS. And again, SRv6 is segment routing using the IPv6 data plane. And we can either encode those labels in a routing extension header, which is part of the RFC 2460 IPv6, or we can actually encode them directly in the IPv6 address. And that's a discussion for another time. So now let's look at the routing architecture in practice. The first thing you'll probably notice, if you're comfortable with MPLS or no MPLS at all, is every router here is using the same exact label value to reach router 5, and that is 16,005 in this case, or node 5. In LDP and RSVP, those label values are dynamically assigned. So router 2 would dynamically assign a label value to router 5 and advertise it to its neighbors 1 and 4, and so on and so forth through the network. So that means every single router is using a different routing label to reach router 5, which means the label changes throughout the network, and it's also dynamic. In this case, in segment routing, what we do is we take an index and we add it to a base. In this case, the base is 16,000. And router 5 advertises 16,005 to the rest of the network. And the way he advertises it is in ISIS and OSPF. And if you're familiar with that, you're going to use an LSA or an LSP, and you're going to flood it throughout the network. So router 5 is flooding his label value throughout the network, and everybody else is learning it. So that means everybody else is going to use the same exact value all the way through the network. So that's really key. And we'll see how that works a little bit more in action. But before we do that, let's look at a simplified version of traffic engineering with SR. Here you'll notice there's 2 label values. So we have a 2 label stack. Now, the one thing we do in segment routing that we didn't do in LDP and RSVP is we assign adjacency labels. So router 4 comes up with dynamic adjacency labels, and he floods them throughout the network. Now, those dynamic adjacency labels are locally significant, which means they're not in the fib or TCAM space or forwarding memory on a router's line card, which means it doesn't waste resources. It's just in the database of ISIS and OSPF, but it is in router 4's fib. So when router 4 advertises it to router 1 and 2 and 3, he's saying, hey, if you want to send a packet or force a packet out my interface to router 5, use this label 24,045. Now that's dynamically assigned. The 45 is just to make it easily readable here. So here, router 1 sends a packet to router 4 with a top label of 16,004. And that is load balanced because we do ECMP with segment routing because it is very IP aware. And then router 4 gets the packet with the top label removed, and he gets 24,045 and forwards it over to router 5. So what we have is a simplified version of traffic engineering. But what you can see right off the bat is you can force a packet over any link that you want because every router in the network will assign a dynamic adjacency label and propagate it throughout the network, and everybody will have knowledge of that and be able to use it. And again, this is all done with ISIS and OSPF, one protocol. Now, when you look at an MPLS packet being forwarded through the network, here we have an SR-MPLS packet, and we're doing the standard operations. We do a push operation at the ingress, it's called label imposition. Then we swap the label through the network, and then we pop it at the last hop, assuming we're doing implicit null in MPLS. If we were doing explicit null, we would leave it on. Again, that's a more in-depth discussion, but if you know what I'm talking about, then you follow me. So you send the label of 16,004 through the network. And if you notice, that label value is not changing. So when you're troubleshooting this in an MPLS or an SR-MPLS network, it's very easy because you're expecting to see 16,004 throughout the network. You don't have to go to each router, look up the dynamically created label values, write them down, and figure out what your label is all the way through the network. Or do a trace route and try to record them. So here, we're seeing the same label value being forwarded through the MPLS data plane. The only difference is the label has been statically assigned by label router 4 and propagated throughout the network, instead of dynamically assigned by all the routers along the path. So let's talk about the single biggest reason that people do SR-MPLS, and that is TILFA, Topology Independent Loop Free Alternate. Yes, I know that's a mouthful. But what that is basically fast reroute. It's 50 millisecond link or node protection with 100% coverage. And it always leverages the post-convergence path. What does that mean? Eventually, a routing protocol converges after a change in the network occurs. That is the post-convergence path. The TI-LFA path, until the network reconverges, is always the post-convergence path. That's not the case with RSVP fast reroute or the old LFA, classic LFA before TI-LFA. And the reason we're able to do this is because we have adjacency labels, and we can force packets out interfaces, get it to the right next hop, and then that next hop will ultimately forward the same original labeled value packet to the final destination. So it's really neat, simple to operate, 2 lines of code on the router, and you're done. It also supports microloop avoidance, and it means no capacity planning. With RSVP fast reroute, you had to do capacity planning. Same thing with DWDM path protection. You got to do capacity planning and see if you have that capacity. Here, we're just saying, hey, you know something? We've got a network. We want to know what the network is in a failed state. And do we have enough bandwidth? Yeah, and that's it. That's all you need to do. Another huge advantage is you can deploy SR-MPLS in parallel with MPLS LDP, and you'll get TI-LFA fast reroute for SR, LDP, and IP traffic. So big plus. Maybe you can see now why the single biggest reason people are deploying this. Plus, a lot of people don't have DWDM anymore or path protection. They don't have old Sonnet path protection. So this makes things really cheap because you're doing it with the existing routers. You're not buying additional hardware, leveraging additional links or wavelengths just to perform 50 millisecond path protection. So looking at the post-convergence path like we talked about, here's a network where we're forwarding a packet from router A to Z. And we're going through link B to C, but link B to C has failed. And as you can see, the link to D is a satellite link because the metric is 10 times higher than the rest of the network. So that's an undesirable path to use. But quite often in a RSVP pass reroute and a classic LFA environment, definitely that path would be used as the fast reroute path. But in a TI-LFA network, we use the post-convergence path. So ultimately, when this network converges, and everybody knows that the link between B and C is down, everybody's using the link between E and F now to get between A and Z. That's the link we're using in a fast reroute condition, which means it doesn't change when we go to a converged state. The only thing that changes is the label stack. And the way we do this is we use those adjacency labels and those segment routing labels to force the packet to F. And then once the packet gets to F, it'll naturally just be forwarded the same way B would forward it to Z, because F's shortest path to Z is through C. So that's how we do it. We force the packet from E to F using one of those adjacency labels we talked about. It lands on F, and then the packet looks like the original packet that left router A before it got to B, and it gets forwarded to Z. I know that's a mouthful, but remember, this is all fully automated by ISIS and OSPF. So you don't have to do anything except for turn it on. Understanding it is nice, but it's not a requirement to deploy it. And again, no capacity planning. So let's talk about SRTE, next single biggest reason that segment routing is deployed. This is not the old RSVP TE, classic traffic engineering, which was very cumbersome, very chatty. This is a brand new traffic engineering with support for all useful optimizations and constraints, including bandwidth, latency, disjointness, and resource avoidance. So we're no longer routing just upon the bandwidth of the network. We can real-time measure the delay with something called performance monitoring. We can propagate those values with ISIS and OSPF, and they become values associated with the link, just like the cost of the link in ISIS and OSPF. And we can do delay-based routing. Or we can avoid certain links, because we can mark links that are not desirable to use, and we'll avoid those links. So again, you can see the power of traffic engineering in SRTE. And again, this can be computed locally by each router, which is a distributed model, or centrally by a bandwidth manager or traffic engineering controller. And we have support for each model wherever it makes sense. So SRTE has been redesigned from scratch. Why? Because it's ECMP aware, which is fundamental to IP. It was designed with simplicity, scale, and flexibility in mind. And it was modeled after IP. RSVP-TE was modeled after ATM and frame relay. If you're familiar with those technologies, they're circuit-style technologies. They're not ECMP aware. That's why all the algorithms were redefined from scratch, leveraging ECMP and minimizing the SID list depth, which means the label stack in SR-MPLS is relatively small in almost all cases because we're going to just send the packet, let it be load balanced, and then when we need to force it along a particular link or path, we'll do that. But otherwise, we'll take advantage of ECMP. And we support dynamic or explicit paths. Operator can explicitly set a path from point A to point B and forward it the way he wants, with knowing that that path will never change from where he wants it to be. But he can have a backup path just in case. The dynamic paths are going to be calculated by the head-end router or a traffic engineering controller. And again, SR and SRTE architecture applies to MPLS and IPv6 data plane implementations. There's also something called FlexAlgo, which provides simplified SRTE model. Very popular because it's really simple. You put some values on routers and you don't put the same values on all your routers. And basically you can slice your network up into different slices. So if you've heard about the term 5G slicing in service provider networks, that's where FlexAlgo can come into play. It also can be used in video delivery networks where you need dual streams at the exact same time that are never going to cross the same links. And I'll show a use case of that. So let's talk now about SR-MPLS in the enterprise. So the first thing people think of SR-MPLS, or SR, segment routing, that's service provider technology. This is a slide from Cisco Systems without the numbers, just percentages. You can see right off the bat that non-SP deployments in enterprises is just as large as it is service providers. So there's a lot of traction of segment routing in the enterprise. This is not just a service provider technology. So why do we need SR-MPLS in the enterprise? We need fast failover via TLFA. Why? Because we have video, voice, real-time data, and now we have AI driving the need for faster route. No one wants to wait 1 second, maybe even 2 seconds for a large network to converge. 50 milliseconds meets our requirements for basically all traffic. So TLFA is very attractive for that reason in enterprises. Plus, we don't need to use DWDM path protection, which reduces cost and complexity and doesn't require pre-planning. It's all native to the IP network that we've built. And SRTE is a stateless solution with the path encoded in the packet. Very simple to deploy and very high scalability throughout the network because, again, it's source routing and we encode this minimal label stack to forward the packet through the network. So looking further into SRTE and some of the advantages, we have explicit path control like we mentioned previously, but that allows the operator to steer the traffic along a specific path exactly the way he wants it, avoiding whatever links or nodes he doesn't want to, and forward the traffic exactly the way he wants. Or he can go to the router and say, give me the best path. Give me the shortest delay path through the network. And if it changes, it's going to be automatically updated. So we get bandwidth routing, we get delay-based routing, and we can get constraint-based routing, which makes things much more powerful and flexible. And we also get per-flow-based traffic engineering, a new feature out there that allows us not only to route the traffic based upon the destination, because traffic engineering routes based on the destination, just like an IP routed packet, but we can also route based upon source information, source IP, markings in the packet, QoS markings. Again, much more granular flexibility. And SRT can be used in enterprise networks to improve quality of service, enhance network performance, and optimize network traffic. It gives the network operator greater control and flexibility in managing his network, and it enables him to meet the demands of modern networks and address the growing requirements for AI. This is a link at the bottom that just is an article that I wrote on this same topic if you want to check it out. So let's look at some use cases. So the most obvious use case is the layer 3 and layer 2 VPN. So the point of this slide is that SR-MPLS is just like MPLS. The same thing you did with layer 2 and layer 3 VPNs and MPLS will be done in SR-MPLS because the data plane hasn't changed. This particular example is a utility pushing their management, voice, video, AMI, and SCADA traffic over 5 separate VPNs for isolation. This could be finance, accounting, HR, whatever it might be, just for segregation throughout the WAN. So that's where you get the layer 3 VPN capability. And you get the layer 2 VPN capability too, if you want to use build pseudo wires across your network and make your network look like a layer 2 network. So again, that's all available to service providers, federal enterprises to isolate networks and departments. Data plan affinity. So this is a common use case for video delivery. It could also be for like 5G slicing. But what we have is two separate data planes. This is usually implemented with FlexAlgo. And what happens is the lower number nodes, the 11, 12, 13, and 14 are in one plane, and the 21, 22, 23, and 24 are in another plane, the blue and red plane. And there's no overlap. So when router 2 forwards the packet, he forwards them across two data planes that never have any node or link overlap. So we have two streams being delivered, and in a video network, quite often video providers will grab both streams and they'll pull frames from both streams if there's noise or something in one stream or another and rebuild it before they put it at the tail end. And this gives you that ultimate flexibility across the network from the head end to the tail end. Again, this is done with a simple SID list and ECMP in mind. So router 2 can forward the packet to 11, and 11 will load balance to 12 and 13. So that makes the SID list or the MPLS label stack very small. You don't have to enumerate these massive RSVP-TE tunnels. You get ECMP natively. Again, very common for multicast video, cell backhaul, and real-time data. Service disjointness from the same head end. Here we have router 1 trying to send a packet to router 7, and we want service disjointness. This is very common for cell backhaul where wire providers like cable providers are asked by mobile carriers to give them backhaul connectivity for their cell network, and they don't want it to traverse common links or common nodes. Here we do this automatically on router 1. We just say build 2 paths, and we give both paths the same ID value, and that means router 1 knows that when he builds those paths, they can't use the same links or nodes, and he computes the paths and sends the packet from router 1 to 7. Now, the thing to note, this is all done by router 1 with no need for a controller. But if we want to do this from two nodes, like say 1A and 1B, we want disjointness, then we would have 1A and 1B connect to a traffic engineering controller, and they both would request that path to 7, and they would both get disjoint paths because the controller would make sure they're disjoint. Again, no core state, and you can see the SID lists are relatively small, 2 and 3 labels, and that's it. So just some resources and next steps. If you want to request a segment routing workshop, you can do that here. You can learn more about segment routing at this link here. We have articles, labs, and video. We have virtual labs running XRV9000, in some cases Juniper. We even have some Nokia ones. And you can learn more about segment routing. We have some that show you ISIS and OSPF from the ground up. And we have others that are more in depth like SRTE. And we have some SRv6 stuff coming pretty soon. And then there's the public repository, segmentrouting.net. You can always check that out. And again, feel free to contact us at any time. We're more than willing to help. Thanks again for your time, and I appreciate it. I hope you enjoyed this, and maybe we'll look forward to having an SRv6 session sometime.